Okay, so dear students, welcome back to our today's lecture. So in our today's lecture, we will be discussing about the energy levels of enharmonic oscillator. So in our previous lecture, we have discussed about enharmonic oscillator, and we got an equation for the energy of an enharmonic oscillator, and from that equation we noted how our enharmonic oscillators differs from our harmonic oscillators, and or we can say how our real molecules obeys enharmonicity, yeah, Morse potential curve instead of our Hooke's law. So in today's lecture, we will be learning about some important concept, that is our about fundamental absorption, first overtone, second overtone, and hot bands, etc. So in these energy levels of enharmonic oscillator, we will also be learning about these four important concepts, and let's see how these what are these four important concepts and how are the energy levels of enharmonic oscillator differs from our harmonic oscillator. So let's start with the equation for the energy of an enharmonic oscillator. So we have an equation where the energy of an harmonic oscillator is given by EV is equal to mu plus V plus 1 by 2 omega E bar minus V plus 1 by 2 square omega E bar XE. So this is the equation for the energy of an harmonic oscillator, where this mu is nothing or V is nothing, it's just our vibrational quantum number, and this omega is our oscillation frequency of enharmonicity, and this XE is enharmonicity constant. So this is a constant, and the value of this constant is very, very small. It is around approximately 0.01. So now this is the energy equation for an enharmonic oscillator. Now let's compare the energy of our harmonic oscillator and enharmonic oscillator. And again, let's try to find the value of different vibrational quantum number. So if I compare the energy levels of simple harmonic oscillator and enharmonic oscillator, so it will if we compare these two, it will become very easy for us to understand what are the difference between simple harmonic oscillator and enharmonic oscillator. So for a simple harmonic oscillator, we have the equation EV is equal to mu plus 1 by 2 omega oscillation bar. And for we have enharmonic oscillator, we have the equation, the above equation, that is mu plus 1 by 2 omega E bar minus V plus 1 by 2 square omega E XE or omega XE bar XE or omega E bar. Now let's substitute the value of V, that is the vibrational quantum number, and we know the V has a value starting from 0, 1, 2, 3, 4, 5, 6, and so on. So this V, the vibrational quantum number, takes the integral value. So if I first substitute the value of V is 0, then what will happen to my energy equation? So when EV is equal to 0, this equation will become, if I substitute 0 in place of V, I will get the value of E0 is half of omega oscillation bar. Again, if I substitute V is equal to 1, what I will get is 1 plus 1 by 2, that is 2, 1, 2, and 3. 3 by 2 omega oscillation bar. So like this, if I substitute V is equal to 2, the equation will become 2 to 4 plus 1, that is 5 by 2 omega oscillation bar. Likewise, if I substitute V is equal to 3, then the equation will become 7/2 omega oscillation bar. So this is the energy I am getting from for a simple harmonic oscillator. Now, if I look on the equation for the energy of an harmonic oscillator, the first term is very much similar to very much similar to the energy of simple harmonic oscillator. Now here I have a second term which is a positive number, and the positive number will increase as the square of this vibrational quantum number, and it will not much affected by the value of this xe, because we know the value of xe is very small term and it is around 0.01. So this much value is not going to affect much on the energy levels. However, the square term of this vibrational quantum number will affect the energy level, and it will the value of this will affect much more as we increase the value of our vibrational quantum number. So let's calculate. First, I will substitute V is equal to 0. Then what will be my equation is V is 0 plus 1/2. It will be 1/2 omega E bar. And similarly, the second term will be 0 plus 1/2. That is 1/2, and 1/2 square is 1/4 omega E bar xe. Likewise, if I substitute the vibrational quantum number is 1, the equation will become 1 plus 1/2. That is 3/2 omega E bar. The second term will be, this is 1 plus 1, that is 3, and 9/4 omega E bar xe. Likewise, if I substitute V is equal to 2, this will become 5/2 omega E bar, and the second term will be 25 divided by 2 and 4 omega E bar xe. Likewise, if I substitute V is equal to 3, the equation will be 7/2 omega E bar minus 49 divided by 2 omega E bar xe. So if we compare these two, the energy of a simple harmonic oscillator and the energy of this enharmonic oscillator, the first term in case of enharmonic oscillator, that is this part, is very much similar to our harmonic oscillator, and the second term is increasing as the value of vibrational quantum number increases. For example, if the vibrational quantum number value is 0, the value becomes 1/4 omega E xe. However, if the value of this vibrational quantum number increases from 0 to 3, our value of this second term is also increasing, and here it is. Here it is 4. It is around 49.4. So this is a positive term. This is a positive term, and also our enharmonic constant is a positive term. So what will happen? As the vibrational quantum number increases, the value of the second term is also increasing. So what will happen? The effect of this, that the vibrational energy levels, the gap between the vibrational energy level decreases as the vibrational quantum number increases. So we will get a energy level diagram like this. So again, if we compare the vibrational energy levels of simple harmonic oscillator and enharmonic oscillator, it will be like this. We know that if we plot energy versus internuclear distances, here also energy versus internuclear distances. So for a simple harmonic oscillator, we know that we got a parabolic curve. For a simple harmonic oscillator, we have the parabolic curve. However, for the enharmonic oscillator, we know that we have a non-parabolic curve, or I can say the parabolic curve get distorted at a particular level where this level is equivalent to our dissociation energy. And here we say that the molecule, the bond breakdown. And again, in case of harmonic oscillator, we know that the energy gap between two energy levels remains constant. The energy gap between two energy levels remains constant, and that gap is equivalent to our omega oscillation bar. However, in case of enharmonic oscillator, we have seen that the second term, the value of the second term increases as the value of the vibrational quantum number increases. So in this case, we will not get a similar gap between the energy level, and the energy gap decreases as the vibrational quantum number increases up to the level of our dissociation constant. So the energy gap between the successive energy levels is decreasing like this as the vibrational quantum number is increasing. That V is equal to 0 to 1, then 2, then we have 3, then we have 4, then we have 5, then V is equal to 6, and V is equal to 7. And our vibrational quantum number ultimately decreases up to the level of our dissociation energy. And finally, the bond breaks down when the energy level reached up to this point, that is our dissociation energy. So this is how the vibrational energy levels of a simple harmonic oscillator and Enharmonic oscillator differs. Thus, we say that as we go into higher and higher vibrational energies, the energy levels are getting closer and closer together as we approach the dissociation limit. And finally, when we approach the dissociation limit, our vibrational energy becomes more closer and closer. So this is the difference between our simple harmonic oscillator and our enharmonic oscillator. Now, we have already known that the energy levels, the energy of energy, the energy of any levels. Now, if we have known the energy of any energy level, now we know the energy of any level here also. Now we can calculate the frequency of this transaction. We can easily calculate the frequency of this transaction. And for that, we must know about the selection rule for our enharmonic oscillator. So important here is the selection rule. So the selection rule for the enharmonic oscillator is that the delta mu is equal to plus minus 1, plus minus 2, plus minus 3, and so on. However, as we increasing beyond this plus minus 3, the population of the molecule in that energy levels are very less, and usually we do not get beyond plus 3 or plus 2. So, however, if we see the selection rules for our vibration, this a simple harmonic oscillator, the values become plus minus 1 only. So the difference between the selection rule between simple harmonic and oscillator and enharmonic oscillator is that for enharmonic oscillator, the selection rule, that is the transaction, the probability of transaction can go beyond plus minus 1. So let's see. Let's substitute the value of this plus minus 1 and see what we will get the fundamental frequencies here. So firstly, if I take the transaction from our V0 to V1, it means that my molecules are undergoing transaction from 0 level, that is the 0 energy level, to V1. And here the I can say that what we are taking the selection rule is that V is equal to plus minus 1 or plus 1. So the first transaction we will get with a considerable intensity, and what will be the value of the energy is what we have to do is we have to make the E1 minus E0. So what I have to do here is EV is equal to 1 minus EV is equal to 0. So I have all the values of these energy levels. So the value of E1 and E2 are here. So what I am doing here, I am subtracting E0 from E1. So what will be the value of E1 is already we have calculated these values, and we know that when we substitute the vibrational quantum number as 1, I have the value 3/2 omega E bar minus 9/4 omega E bar XE. minus V is equal to 0, which is 1 by 2 omega E bar minus 1 by 4 omega E bar XE. So when I solve this equation, what I will do is I will bring these similar variables on one side. For example, I have omega E term and omega E XE term. So I will bring together the omega XE term, the omega E term, though I have 3 by 2 omega E, and here I have 1 by 2 omega E minus 1 by 2 omega E. Similarly, the second term 9 by 4 omega E bar XE minus minus plus, it will become 1 by 4 omega E bar XE. So when we will solve this equation, the bases are same. What I will get here is 3 minus 1, 2, 2 by 2 omega E bar minus, here again bases are same, plus minus 9 plus 1, it will be 8 by 4 omega E bar XE. Then we can cancel these 2 and 4, 1, 4, 2, 8. The equation will become omega E bar minus 2 omega E bar XE. So from this equation, I can take omega E is common. When I will take omega E bar is common, the equation will become 1 minus 2xe, 2xe. Centimeter inverse. So I got every first equation in which our energy, that is EV minus delta EV, is equal to omega E bar into 1 minus 2xe, and this equation is known as our fundamental frequency or fundamental absorption. So what we mean by fundamental of absorption is when the transaction takes place from 0 energy level to first energy level, that value will correspond to our fundamental absorption, and this absorption will get with considerable intensity. Considerable intensity, it means the transaction will appear with a very good intensity. So this differs. So here if we see, in case of harmonic oscillator, we have got that delta E is equal to omega oscillation bar. However, in case of enharmonicity, what we have is we have omega E bar, but along with this omega E bar, we have the second term 1 minus 2xe. So this is the basic difference between our harmonic oscillator and enharmonic oscillator. So what will happen, the effect of this second term is this, that the fundamental thing is that the energy levels are not equally spaced, as we have seen earlier, and as we approach the dissociation constant in the graph, the levels get closer and closer and closer. So we can imagine that there is a maximum vibrational quantum number beyond which it dissociates. So if we see the plot here, we can see that up to this point, we will get the maximum value of our quantum numbers. So beyond that, our molecule will dissociate. So up to this dissociation constant value, we can get the maximum level of our quantum number. So here we got the first transaction. It means, this means that if this is the energy levels diagram of enharmonic oscillator, so this is V is equal to 0, then V is equal to 1, then is equal to 2, then V is equal to 2, 3, then slowly the energy gap will decrease and it will completely distort it at this point. So this is our fundamental absorption. Fundamental absorption means when we put the value of this vibrational quantum number is 1, so this means that the transaction are taking place from V0 to V1, which is very similar to what we have for our simple harmonic oscillator. So here we have the delta V is equal to plus minus 2, plus minus 3, and so on. So if we take the value of this vibrational quantum number as V0, it means that the transaction is taking place from V is equal to 0 to V is equal to 2 also. What we mean by delta plus minus 2 means that usually earlier cases we have only saw that the transaction can only take place from one vibrational to the second, the upper vibrational level. However, in case of enharmonic oscillator, the transaction can also occur from V0 to V2, V0 to V3. But due to the population difference, due to the higher energy difference, the intensity remains very low. So if I see the value of the second transaction, that is when my V0 to V2, the transaction is taking place from our ground energy level to second energy level, it means the delta V is plus 2 or minus 2. But the intensity remains very small. So that if I got a peak for this, the intensity of this is very small. So I can say I can get a peak, but the intensity of that peak becomes very small. So the delta E becomes, what I have to do is I have to make V2 minus V0, and I know the E2 minus E0, V2 minus EV is equal to 0. So I have the value of this energy level 2, which is 5 by 2 omega E bar minus 25 by 2 omega E bar XE. I have to subtract this from our V is equal to 0 energy level, which is 1 by 2 omega E bar minus 1 by 4 omega E bar XE. So again, let's bring the same terms together. That is 5 by 2 omega E minus 1 by 2 omega E bar minus 25 by 2 omega E bar XE plus 1 by 4 omega E bar XE. Okay, 25 by 4, it is 4. So if I solve this, then what I will get from here is base are same. Here 5 minus 1, 4 by 2 omega E bar. Likewise here, this is our 25, and this is our 4. So what I will get here is 24 divided by 4 omega E bar XE. So if I can cancel this 2 to 2, 4, 4 is and 4, 6. So what I will get here is 2 omega E minus 6 omega E bar XE. I can take 2 omega E bar as common. What I will remain here is 1 minus 3 XE centimeter inverse. So the probability of the second transaction, when the transaction is taking place from V0 to V2, I have an equation that energy will be equal to 2 omega E bar 1 minus 3 XE centimeter inverse, and this is known as the first overtone. This is known as our first overtone. So this is the first overtone. The first overtone is the transaction in which the transaction is occurring from our V is equal to 0 to V is equal to 1 state. So if I draw the transaction here, is that the transaction is taking place from V0 to V2. So this is our first overtone. Similarly, if our transaction can take place from V0 to, that is the third probability, is if the transaction can take place from V0 to V3. The energy will become, we have to subtract EV is equal to 3 minus delta EV is equal to 0. So again, we have the values 7 by 2 omega E bar minus 49 by 4 omega E bar XE minus 1 by 2 omega E bar minus 1 by 4 omega E bar XE. So if we calculate these two, this will become 3 omega E 1 minus 4 XE centimeter inverse. So This is the energy when the transaction is taking place from the ground state level to our third energy level, when the transaction is taking place from V0 to V3, and this is known as second overtone, and the transaction here can happen from our V0 to V3, that is V is equal to 3. So these three transactions can be possible, but beyond this can also be possible, but the higher energy gaps, due to higher energy gaps, the probability of this transaction is very minimum, and even if it occurs, the intensity of the peak remains very low. So the intensity here further decreases, the intensity of peak further decreases in case of our second overtone. So what this means is that we can get different peak in the spectrum. So this is we can easily show this transaction is like this, that these are the energy levels. For example, this is the V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3, and the energy gap further decreases like this till the dissociation constant. So these three transaction is, the first one is from here to here, second is from here to here, and third is from here to here. So the first one peak is known as fundamental absorption, second is first overtone, and the third is our second overtone. So what will the effect of this in the spectrum is that we can get different peaks. For example, the first peak I got his here at omega E bar. Second peak I will get near to omega E bar. Third, I will get around 3 omega E bar. So you can get different peak in the FTIR, which is the real sense of a real FTIR of a real molecule, but the intensity of these peaks start diminishing as we move from the fundamental absorption to first overtone and the second overtone. So this is how our actually the FTIR spectra appears in case of real molecules. So these three important concepts we have seen here, that what do we mean by fundamental absorption. Then the fundamental absorption is that absorption which will appear near this omega E bar. The first overtone appears somewhat near this 2 omega E bar, and the third of the second overtone will appear somewhat near these 3 omega E bar. So the first fundamental absorption means when the transaction is taking place from ground state to first state. First overtone means when the transaction is taking place from 0 to second. Then third is 0 to third. So this is what we mean by fundamental absorption, first overtone and second overtone. Beyond that, the transaction can also take place from our higher energy levels. So the transaction can also take place from V1 to V2, V1 to V3 also. But we know that the population, the maximum population of the molecules will remain at the ground state only. The number of molecules present in the first higher energy levels is very minimum. If even the transaction can occurs from V is equal to 1 to V is equal to 2, the intensity of these peaks remains very, very, very low. If we can see the population difference between V0 to V1, the population difference here is NV is equal to 1 to NV is equal to 0, and this we can get by solving the Boltzmann distribution or equation. The value of this is around 0.008. It means only the 10% of the molecules present in the ground state level will be available in the first energy levels. So the transaction can occur from V is equal to V1, V is equal to 1 to V is equal to 2, but due to the population difference between V0 to V1, even the probability of this transaction is very less. Even if we can see the difference energy difference between these two levels is, if we can calculate the delta E for delta E V is equal to 1 to I can say V is equal to 2. If we have to find this transition where our delta mu is changing by plus minus 1. So usually this can you can get some weak intensity peak for this, and we can identify this peak by varying the temperature. So if I have to find the energy difference between these two, what I have to do, I have to subtract the energy of vibrational quantum number 1 from vibrational quantum number 2, which I have all the values. The V2 is equal to our 5 by 2 omega E minus 25 by 4 omega E bar XE minus 1 is 3 by 2 omega E bar divided by 9 by 4 omega E bar XE. So if you solve this equation, what you will get from here is, again, combine the similar term, you will get a equation where delta E is equal to omega E bar 1 minus 4 XE centimeter inverse. And this equation is known as, or the band appears due to this transaction is known as hot bands. हॉट बैंड, तो इसको हम हॉट बैंड कहते हैं जब आपका ट्रांसैक्शन फ्रॉम V is equal to 1 to higher energy levels में ट्रांसैक्शन होते हैं. And peak, so you can get a peak, but the intensity of these peaks remains very low, or and the position of these bands appear near somewhere near your fundamental absorption band. So if you have to identify about these hot bands, what you have to do is you have to increase the temperature. You have to increase the temperature. So when you increase the temperature, the molecule will move from your ground state, that is mu is equal to 0 to mu is equal to 1 state. Or I can say, if you increase the temperature of this system, the kinetic energy of the molecule increases, and some molecule from your ground state will excite it to your first excited state. And we know that the intensity is directly proportional to the population. If you increase the temperature, the intensity of the hot band also increases. So by increasing the temperature of the sample, you can identify between the hot bands and the normal fundamental absorption band. So again, the fundamental absorption band is here and hot band will appear somewhere near here. So if you have to identify between the fundamental absorption and the hot band, you have to increase the temperature, and if the increase in temperature increases the intensity of this peak, it means this peak is the hot band, not the fundamental absorption. So this is all about our energy levels of enharmonic oscillator. So again, if we take the example of HCl, in case of HCl, we got 3 different peaks. One is around 2886, second is 85668 centimeter inverse, and the third 8347 centimeter inverse. And this is due to the fundamental absorption, this is due to first overtone, and this is due to second overtone. So in the actual spectrum of HCl, we can get these many peaks for our HCl. However, if we talk the case of our simple harmonic oscillator, we should get only one peak because the gap between the energy levels are very similar, that is equal to omega oscillation per. So from here you can calculate the oscillation enharmonic oscillation frequency, that is omega E bar. Now if I can assign this peak to our HCl molecule, so the first peak is around 2886, and this is for our fundamental absorption, the value of which is 1 minus 2 XE. The second value I can easily assign for our first tone, which is equal to 2 omega E bar 1 minus 3 XE. And the third peak I can assign to the second overtone, which is 3 omega E bar 1 minus 4xe. So from here, we know that the value of xe is very, very small. We can calculate the value of this frequency, that is enharmonic oscillation frequency. And if you have this enharmonic oscillation frequency, you can easily calculate the value of force constant by using this equation c square mu. So by using this equation, you can calculate the force constant or the strength of any bond. So that's is all for today, and it is all about the energy levels of enharmonic oscillator. Thank you for today.